Hello, everybody. My name is Samuel Lopez. I am an applications engineer at Ozen Engineering. And today I'm going to be talking to you guys about how to set up parameterized models in Ansys Workbench and in Ansys Mechanical. Now, generally, there are a couple of different ways we can go about this. The easiest way to create parameterized models is to use what we call Design Explorer, which is kind of an inbuilt tool from within Workbench itself. It essentially allows us to define parameters in all sorts of ways, things like geometry parameters or boundary condition parameters, things like that. Those all manifest themselves in what we call design of experiments, which is essentially just a large table of values that we can change the values for the input parameters on to then tell us how those input parameters are going to affect our output parameters. It's the simplest way to run a large design of experiment study or a large parameterized model to try and optimize different values. But it's a little bit of a manual process because you have to go through and manually change all of those input parameters. The second way that we can go about doing this is using a different tool called OptiSlang. Now, OptiSlang, what it does is it's a separate tool add-on that we can combine with our design of experiments setup to try and help us set objectives to optimize our model that way. OptiSlang is a little bit different from what we're going to be looking at today. It's a separate tool that we'll make a video on for as kind of a follow-up to this later. So that's the second way we can go about using these parameterized models. The third way is using something called space claim scripting. Now, space claim scripting is also a little bit outside the scope of what this video is going to present. We'll make, again, another follow-up video showing how to go about setting up models using space claim scripting as another follow-up to this video. So what we're going to be focusing on today is just the main aspects of using design, what we call Ansys Design Explorer. Okay. Now, the first thing that we're going to do is we're just going to take just a basic model. We're going to be doing a coupled field static model, which just means we're running multi-physics capabilities for this specific case. In this example, I'm going to be using just a basic heat exchanger model. We'll kind of get to that in just a moment. This heat exchanger model is available from Ansys Discovery. So everybody, as long as you have Discovery, you should have access to the same CAD model that I'm using for the purposes of this demonstration. And we're going to be covering all aspects of things that can and cannot be parameterized. So the first step that we're going to do here, or the first step that you would want to do if you were trying to follow along with this example, is to drag in just a generic coupled field static model and then link it to something upstream called the Granta selector. Now, Granta selector is also a separate add-on tool, but what it is essentially just a large materials database that gives us access to more materials than the regular Ansys Mechanical Materials database has inside of its libraries. And since materials are one variable that we can use for parameterization, I thought it useful to show how to combine to an even larger database such as Granta, so we can see how not only adding these new materials from this larger database works, but also how we would then go about parameterizing that material to make sure that we can use these things later on in the analysis. So the first step that we're going to do here in defining our parameterized model is to choose the materials that we would want to be analyzing for this specific design of experiments. So the first thing we do is we go ahead and open up Granta Selector, which I'll do right now. When Granta Selector is open, what you'll have to do is you'll have to search the materials library to find the material that you want. So when it opens, it's going to look a little bit something like this. Now, depending on what packages you may have, Granta Selector, as you can see, has a wide range of different materials packages that you can get access to, depending on what kind of materials you'd like to be able to use. you can add different materials or look at the different material properties from within here. So if I start opening these folders, and there's going to be a lot of different subfolders here, once I find a material, if I want to see what the properties are for that material are, I can just double click and I can look down and I can scroll down until I get my mechanical properties here. These granted materials have a lot of different material properties, as you can see. They have thermal properties, mechanical properties, electrical properties, etc. And all of this information can be imported to Workbench automatically so that we can use it. In this specific example, the material that I'm going to be using is a graphite material. And so rather than kind of look through all of these individual folders, what I'm going to do is I'm going to use my search function here, and I'm just going to type in graphite. And once I do that, I can see all the different folders or all the different databases I have in Granta that give me a result for, a type of graphite that exists in that specific folder or for that specific database. For this example, I'm going to be using like a premium type graphite, which is available from within this material universe package here. And so I scroll down until I find the type of graphite that I want. And it turns out that it's going to be this one. And so what I would need to do here, now that I've identified the material that I'd like to use for this analysis, I would want to right click and then export this material to the engineering data. Now, once I click on that, if I come back here in a Workbench, what I should see is that this Granta selector branch would have a update symbol on it. So I need to update this. And then once I do that, then my engineering data should also get updated. And now I should see that I have my same graphite premium material that I added from Granta into my Ansys Workbench materials list. So all of these materials are materials that I want to be able to use potentially as parameters for this analysis. The first type of graphite, this one here, I grabbed from just the default engineering data sources library here. So if I click on this, there in one of these libraries, there's this this graphite pure material that I can use. And for the extra type of graphite here that we just added, this one comes from that Granta, as you just saw, the Granta selector tool. This alumina also comes from within the engineering data sources library here. So now that I've got my material set, the next thing we want to do is we want to go ahead and edit our geometry. And to do that, we're going to be using Ansys Discovery. So we'll go ahead and open Discovery here, and you can see I've already got my model kind of preset. As I mentioned in the beginning, it's this heat exchanger model is the same heat exchanger model that Discovery uses for its kind of tutorials that it allows for when you're first kind of getting started with Discovery. If you want to access this specific CAD file, what you can do is you can go to the File option here, click on the Home Page button, and then go over here to the Samples option. And it's actually this heat-sink thermal model here that I'm using. Now, one thing to note is that this heat-sink thermal is like a fluids type simulation in Discovery. So what I've done is I'm just using the solid portion of that analysis or of that CAD model, and I've actually suppressed my enclosure around it, my fluids enclosure that goes around this heat exchanger and does the CFD part of the analysis. As I'd mentioned in the beginning, we're going to be doing coupled field, and the two types of physics that we're going to be solving are heat transfer, but mechanical heat transfer, so thermal type physics, and structural type physics together in the same block. Because I'm doing a heat transfer in mechanical, I don't need to include surrounding enclosure like I would need to if it was a CFD type heat transfer analysis. And so that's why I'm suppressing it for the purposes of this demonstration. In case you're unfamiliar with Discovery, there's a lot of starter information available on Discovery from the Discovery forum. Or you can look at our homepage, which should consist of some other videos and introductory material for getting started with things like discovery and space claim and other CAD tools that Ansys has to offer. So getting started with discovery here, we've got our CAD model imported. This is just, again, our basic solid model. And now we want to determine how we can go about parameterizing this. Now, from a CAD perspective, the things that we're going to parameterize at this stage are what we call geometrical input parameters, right? So in other words, what we're going to be doing is changing the geometrical parameters associated with this CAD model. And what I mean by that is we can change things about this model related to its specific shape, size, patterns, things like that. So let's say, for example, one of the things we wanted to do or analyze for this specific model is how much heat is going to be released from this heat exchanger based on the size of all of these fins, right? Now, in order to do that, what we would need to do is we would need to run a series of analyses where the height of these fins are changed. Maybe we start off with an arbitrarily small value and we kind of work our way up to some maximum, and then run the simulation for all of those individual cases to determine kind of which value or which height of fins gives us the kind of optimal heat transfer values that we would want to include, right? So to do that, what we would need to do is to create a parameter such that we can manually change the height of those fins, right? Otherwise, what we would have to do is manually come back and adjust each individual model, right? So in Workbench, what we would have to do is come back, change the height, run a model, and then change it again and run it again, and so on and so forth. We don't want to do that. It's going to be too time consuming. And so that's what we use parameters for, is to help us kind of automate that process. And the way that that works is we can use these different tools from within the design tab of discovery here to help facilitate that. In this example, if we're going to want to vary the height of these fins here, what we can do is we can use our move tool. Now, our move tool essentially does exactly what it sounds like, right? It allows us to pick different things like surfaces and either translate or rotate them in three-dimensional space, or we can orient them with respect to an object and create parameters. For this specific example, as I'd mentioned, what I want to do is I want to vary the height of these fins. And so what I'm going to do is I'm going to rotate kind of normal or perpendicular, I should say, to the height of these fins. And then I'm going to draw a box by left mouse boxing from left to right here, and box selecting all the top surfaces of these fins, just like this. And now that I've done that, if I've got the move tool selected, I can see that I've got this axis that shows up. Because I want to change the height of these fins, the only direction that's going to be affected in this case is the Z direction, this blue direction here. And so if I don't want to change the X or Y, I don't have to worry about this. And so what I can do is I can directly select my Z axis here. And now in the options of my move tool, I have the option to pick my ruler, which allows me to select a point of reference. Since I want to be able to change the height of these fins, what the reference that I want to select is going to be kind of the inside base of my heat exchanger, right? Because that's going to determine what the overall height of these fins are. And so you can see as I kind of move up and down, I have this little yellow ball next to my cursor. That little yellow ball is going to be where I'm actually setting my reference. If I kind of scroll down and highlight over this bottom surface here of my, or I guess I should say the top surface of my heat exchanger, and kind of rotate this a bit, I can see that if I click this surface, that's where it's going to select my reference or my point of reference. And so that's what I'm going to do is I'm just going to left select this top surface here. And now that that's done, if I move away, you can see the yellow ball no longer is following my mouse. And now what I can do is I can click on this little button here, which is going to allow us to actually enter this selection as a parameter. So if I click this, now we can see I have this little button over here. And if I click on it down here in Discovery, then I have the option to view this from within all the different parameters that I've defined, right? Or from within what we call the parameter window. We can choose to name it whatever we want. So in this example, what I'm going to call it is fin height. And now if I change this, what I can see is that when I hit enter, the height of these fins should change relative to that same reference point that I just defined, right? So what we're doing here is we're not extending from where it was originally an additional 50 millimeters. What we're doing is we're setting the total height of these fins relative to the top surface of this heat exchanger. And to prove that, what you can do is you can go to the measure tab over here, and you can click on the measure tool, and we can measure the length of one of these lines, because this line should give us the total length of the height of these fins. If I look over here, I can see that that line length gives me a total of 50 millimeters, which is exactly what I defined in my parameters. And so I know that the way that I've defined this from within my parameter set is correct. And so with that selected, what I'm going to do is I'm going to hit escape there to get off of the measure tool, and I'm going to change this value back to what it originally was. It was about 35 or so. So I'll hit 35 and hit enter. I think it was 25 actually. Do 25. There we go. That looks better. So I'll change it back to its original value, and I'll close out of this box for now. So that's one simple, one-dimensional parameter that we can change, right? Another type of parameter, another thing that we can change, let's say we don't have a super obvious reference point, right? Let's say that we want to vary the length of this heat exchanger as well. Okay, so in that example, what we would need to do is we would need to set some kind of reference point, right? And the reference point can either be kind of the other side of this heat exchanger here, like I used for the height of my fins, or it can be some arbitrary point in the center. Now, the tricky part is if I extend this surface, right, if I extend the length of my heat exchanger, let's say another, I don't know, 50 millimeters, like I did the height of those fins, right? I can easily do that just by pulling the surface, but the problem is going to be that my origin here in SpaceClaim is going to stay the same if I make my reference the other side of this model. And depending on what you're trying to accomplish in your analysis, sometimes when you run your model, you depend very heavily on the orientation of your model with respect to the origin. And so what you can choose to do is you can choose to use the origin as your point of reference as well. Now, in this case, what I'm going to do, I'm going to come back here to the design tool. And instead of move, what I'm going to do is I'm going to use the pull tool. Pull works much the same way that move does, except we only have the option to move in one direction. So if I click on this surface here, you can see that I'm only allowed to move in the kind of perpendicular direction to this surface. I can't move along different directions like I can with move. So with pull, it's going to work fairly similar. But what I want to do is I want to also click on this no merge option. Otherwise, it's going to bond this body with all my little kind of power source bodies that I have here on the bottom. So we click no merge, and then we also click on the ruler. And once we click the ruler, we can set our point of reference to the origin just by kind of hovering over it like this. Once I select the origin, it's much the same, where I just add this as a parameter. And once I do that, then my parameters should show up in the table here as well. So again, it's going to name every new parameter, parameter 1. I changed this one to fin height, so this is now parameter 1, but we can adjust this as well to something like fin length. Now, the thing that I have to keep in mind about this specific parameter is that it's only going to give me half of the total length. Okay, so if I change this, and let's change it to 50 again, you can see that it did extend it like I asked it to. It extended it outwards with respect to the origin. But the total length of this is not going to be 100 millimeters, right? Because we only moved this half of the heat exchanger outwards. If I wanted to control the total length, I would need to create another parameter on this side, which pulls this specific side of my heat exchanger outwards with respect to the origin as well. And then doing that would give me control over the total length with respect to the origin at the center of my heat exchanger. Okay? So that's another way that we can go about defining parameters that don't necessarily have um, a reference on the actual CAD model like I did with my first parameter, right? In this example, what we're doing is we're referencing the origin instead. You can also choose to reference different points like we showed on the heat exchanger itself. So you'd be able to pick, for example, maybe this surface here on one of these fins, or some intermediate surface on any one of these, kind of perpendicular here, these wide surfaces, etc. It just kind of depends on what kind of parameter you'd like to set. So that being said, I'm going to change this back, and I'm going to show you a couple of other things that we can do with parameterization objects, right? So another example would be, let's say we want to change, we have the simple things like height, length, width, all of those things pretty easily controllable, right? What about something a little bit more complex like the radius of a circle? If I wanted to change, let's say, the radius of these circles so that I can control, let's say, the size of the bolt that I want to use to secure this heat exchanger, um, then what I would need to do is I would need to use the pull tool. So in this case, what I'm going to do is I want to adjust all four of these at once. I don't want four parameters representing each one of these holes individually. And so what I can do to facilitate that is I can combine these selections by holding control and then selecting all the different holes that I've got here. So you can see there's 1, 2, 3, and I'll have the fourth one in just a minute. So now I've got all four of those holes selected. And now what I can do is I can click on the pull tool. And now I can see that I have this little R symbol next to this hole. It's only going to give me the arrow next to one of them, but all four of them are still selected. The R symbol means that I'm controlling the radius. And now if I click on the add as a parameter button here, and then hit escape to get out of the pull tool, if I open this back up to look at my parameters, now I can see that that value has also been added. So if I increase this to 2 millimeters, then you can see that the diameter, or I guess the radius, of all four of these holes changed simultaneously without me having to go through and change each one individually, right? And that's because we parameterized all of them together instead of each individual one separately. And so that's how, we can control these parameters for other types of geometrical features, like holes. So I'll change this back. I believe it was 1.65. And now we have that, those types of parameters set as well. The last type of parameter that I want to show you that we can add here is actually with regards to patterns. So this is a slight change I made from the original CAD. In the original CAD model, we have these little dies at the bottom of our heat exchanger here, and it's one large die kind of at the center. And what that die is doing is it's providing a power input for this heat exchanger, basically, so that we can see how much heat is being added through that die and how much heat in turn is being removed from the heat exchanger, right? And so what I've done is I've taken this die and I've shrunk it down a little bit, and I moved it up to this top left-hand corner, which is just kind of an arbitrary distance away from each of these. And then what I did is I used a pattern tool here in Discovery to create a pattern of these dies across the entire board. So now what I would be doing essentially, instead of applying the power to one large die here in the center, is I'm applying that same amount of power just spread out amongst all these little dies from within, mechanical here. But if I want to control, let's say, the amount of dies that I have on the bottom, then I would need to parameterize the pattern that I just created. If I click on the top left little die here and also select my pattern, I can see all the different types of variables that I have available to me to control, that also control the overall pattern, right? So we have the total count, which means the number of dies that I have in the X and the Y direction. So in this example, I've got 8 dies going from left to right, so 8 columns of dies, and also 8 rows of dies going from top to bottom. It's a little bit hard to see, but what I've got selected here is controlling the amount of rows that I have going from top to bottom. I've also got the total width up here. So if I click on this, this is going to represent the total width that this pattern is allowed to be created with. And then these values here, these 6s, control the spacing of these actual dies in X and Y, right? So if I click on this value here and kind of zoom in a little bit so it's easier to see, you can see here that from the center point of this die to the center point of its neighbor here is this 6mm value. And the same is true for this value here, just in the vertical direction. So these are how we're controlling the full parameter spec of this pattern. And I can control the features of this, right? I can parameterize this so I can change this however I want. And the rules are essentially the same. If I want to change the number of columns that I have, what I can do is I can click on this value here for the count, and then click on our add parameter button. And now when I come back down here, I can see that I've got this value exposed. So I can change this if I want to change it to 5, for example. And if I change it, then what I can see is it's going to update it automatically, right? Now, what you'll notice is that I've got 5 columns like I've defined, but if I click on this now the other 2 values or the other value, I guess, for my X spacing changed, right? And it had to change because of the way that I've set this parameter up. So if I click on my spacing here, again, this spacing, it has to maintain this 42mm width, right? So from the center point of my original die to the center point of my end die in the X direction, that has to be 42mm. I can control that if I want to by adding that as a parameter as well, or if I wanted to more directly control the spacing, I would be able to set this value as a parameter. And you can see here that we have these little lock values next to some of these items, right? So you can see here that this value is unlocked. This value is now locked because I've created as a parameter. If I click on these other values, you can see that some of them have locks, some of them don't. Now, what that means is that if it's locked, you are not allowed to, with your pattern, to exceed that value, right? So if this 42mm is locked, which right now it is, then no matter how many columns I have, the width between the first one and the last one has to be 42. If it was free, like it is for the X spacing here, that allows me the flexibility to change the dimensions between the center point of this die to the center point of its neighbor, right? So if one of these is locked, right? So if the max value between the first and last is locked, then this one has to be variable because we can't necessarily set both of these things at the same time, right? If the distance between the first and last is 42 and we know we have 5 rows, then that automatically gives us our X spacing, which is why it has to be unlocked, and so on and so forth, right? So that's how we can control our different parameters. So what we'll do is we kind of set up already kind of an arbitrary set of parameters. And once we have all of our parameters set up, then we can go ahead and go back into Workbench. Now, the important thing to keep in mind is that, number one, my Workbench model is already complete. I'm still, again, going to walk you through how I set up all these different input parameters that I have. However, in the interest of time, I've already got this set up, so your model may not look like this. The main difference at this point to what your model looks like versus what mine looks like now is that you won't have this arrow coming from the parameter set that you should now have if you've got these parameters that we've defined at the discovery level. This arrow won't be here. And the reason for that is because what we've just defined are called input parameters, right? And the input parameters are basically going to affect the general setup of the model, right? The way that our model is going to look before we even run it. And so we've already defined input parameters, but we don't have a parameter, what we call a parameter of interest yet, or an output parameter. And so this box, or this arrow coming back to our parameter set, won't yet be there. And to give you a little bit more insight into this, if you double click on this parameter set, you'll see this little window open up here for that parameter set, and it'll list for you all the different input parameters that you have, okay? So for this example, I'm changing things like the hole radius, like we talked about, the fin heights, and I've got, I'm adjusting the heights of all those different sections of the fins. So, these fins on either end, I can control those separate from the ones in the middle. I'm also controlling things like the pattern, right? So the pattern, how many there are in X, how many there are in Y, and what the spacing is there. And then I'm also going to be parameterizing things about my boundary conditions, which I'm going to show you how to set up in just a minute. So all of your parameters, as you define them, are going to slowly start to fill up within here. And for right now, until you're done setting up those parameters, you don't necessarily have to worry about the rest of what's shown in here. So all of this we're going to go over after we finish setting up the rest of our model. Moving into mechanical now, if I open my mechanical model, I can see here that I've got my general setup already completed, right? And the first thing that we need to do when we define our mechanical model is we need to assign materials to each of these individual bodies. Okay, and to do that, we can open the geometry tab here, and then we can choose the component that we want to change. Now, in this example, I've got a lot of dies, right? So all the dies I'm going to leave as just the same default structural steel material that Ansys automatically assigns. But the thing that I do want to change is this heat exchanger, okay? Now, this heat exchanger, I want to change it to be that graphite material that we added earlier from Granta. And I want to parameterize that so I can see the effect of comparing that Granta material to some of the other materials that either we may have gotten from Granta or from the Ansys material database, either or. And the way that we do that is we come down here to the material assignment cell here in my properties, and we click this little box next here to the assignment box, and this little P icon will show up that stands for parameter. Okay, so you can see here that originally I've set it to be that graphite material, but then I'm parameterizing it so that I can control it from back here within Workbench in my parameter set. So if I scroll down here to the bottom, my parameter 15 here, I can see is that heat exchanger material. And I can control it to be whatever I want, right? I can have it be the graphite or the silicon material that you saw, the structural steel, anything, oops, sorry about that. Anything that's within my engineering database here that I've added, I can use to define as a parameter for my heat exchanger here now that I've exposed that as a parameter from within mechanical. If I go back here to mechanical, after I've got my material set, I'm going to go ahead and close this so it's not so big. The next thing we want to be able to control are the different aspects of our boundary conditions. And so the way that I've set this model up, it's pretty straightforward. Again, like I'd mentioned, we're going to be doing both structural and thermal physics on our heat exchanger block here. So that's going to mean that we have to define both structural and thermal boundary conditions on this model in order to fully constrain it. So what I've done here is I'm applying a simple fixed support to all of these kind of outside holes that we were adjusting, right? So no matter what diameter these holes are, I can maintain that it's always going to be a fixed support to define them. And this is actually going to fully constrain my structural degrees of freedom, right? The rest of this is going to be determined by our thermal stress. And so to help define the thermal aspects of this model, what I've done is I've used a constant temperature boundary condition to apply constant heat to the bottoms of these little dies here that make up my pattern. And the temperature that I'm using is 31.5 degrees Celsius, which is roughly 80 degrees Fahrenheit. Just arbitrary values here. If I want to be able to control how much heat I'm adding, right, or what temperature I'm setting these dies to, what I can do is I can come down here into the definition of my temperature boundary condition, and just like we did with our material, I can click this little box next to my temperature magnitude definition, and this little P box will show up again, confirming that I've parameterized this temperature value. Now, this temperature value we're going to be using as what we call our heat source. Okay, so this is how much heat we're going to be adding into our system, because according to our initial conditions here, our initial temperature is going to be starting at room temperature, 22 degrees Celsius. And so we're adding in this heat by having this be higher than that initial room temperature value. So whenever you have a heat source, you have to have a heat sink so that heat can dissipate from your analysis, right? And you don't have everything just be the same temperature. And in this example, what I'm using to define my heat sink is this convection boundary condition. And if I change to standard units, you can see here that what I'm doing is essentially defining natural convection, about 10 watts per meter squared Celsius, and my ambient temperature is just a little bit warmer than room temperature, right? I think I said all of these in US units, which is why these are kind of decimals. And so if I want to control, number one, how much heat I'm removing from this heat sink here, and number two, what the ambient temperature is, which kind of also helps control how much heat is being dissipated to the environment, I can parameterize both of these values from my convection boundary condition, right? The heat exchange, the film coefficient here, if I parameterize this value, it'll allow me to change this in mechanical so that I can choose to either have more heat be rejected to the environment or less heat being rejected to the environment based on how high or how low this value gets set. And the ambient temperature basically just says, you know, what the temperature of the room is so that we know how much heat can be lost to the environment based on whatever our film coefficient is. Okay, so I can control both of these values as parameters. And if I come back in here to Workbench and go to my parameter set, I can see that those two values, in addition to my temperature, are listed here. Now, once you have all of your input parameters set, you'll notice that over here on the right-hand side, this first column here will be populated with the same entries as these input parameters over here on the left, okay? And this is going to be marked with a DP0 or design point 0, okay? And what this means is that this is going to be the first iteration of this problem that we want to consider. If we want to do other iterations of this, then we can basically just click into this box right below it. I guess I should say this box because this is where we're actually defining our conditions here. And we can enter a new value for our design points, right? So if I wanted to, for example, enter a design point 11 here, what I could do is enter any arbitrary value for this parameter, let's say 1.45. This is going to invalidate my study, but that's okay. And once I hit enter, then what you can see is that it's going to automatically populate all of the rest of these values to whatever the original value was, okay? So in this example for design point 11, what I've done is I'm changing the radius of that hole, right? I'm decreasing it to 1.45 millimeters. And all these other parameters are going to be the same as the original. Now I can always come back and edit this. So if I wanted this to be like 19, for example, I can change multiple at a time. But mechanical will automatically populate those for you because all of these design point entries have to have valid input parameters. And so they automatically get copied from whatever design point 0 is. So for however many cases that you want to consider, right? Let's say you have 4 different fin heights that you want to consider. You can enter 4 different design points to be considered for your parameterized study. This table here is going to be, it's called our table of designs, but when in running our model this way, this is what we call our design of experiments, where we're running different parameterized versions of the same model to see how it affects the outputs, okay? Now to this point, if you remember, we haven't set any output parameters yet, and so there's nothing, we're not really optimizing based on anything, we're just changing the inputs of these things. If we want to set an output parameter to basically help us determine how these inputs are affecting our overall results, we can do that by coming back here into mechanical and entering results that we want to use as our output parameters, right? So in this example, what I'm doing is I want to measure the total deformation of my heat exchanger. So after this model is finished running, how much is it basically deforming in a given direction? In this case, this is the magnitude of my total deformation, right? So it's going to be x square root of x squared plus y squared plus z squared. And what I want to take from this is the average value, because there are going to be some places on this model that deform a little bit more than others, and so on and so forth, right? So what I do is I come down here into the results of my total deformation post-processing result, and I click the little box next to the average total deformation value. And now that exposes this value, this average value of total deformation, as an output parameter. Okay, so if I come back in here into mechanical, I can see that now I've got a brand new section here called output parameters, and my total deformation average appears here. You'll also notice that I can't change this like I can my input parameters, because my input parameters are what determine this final value. Okay, so in this example, what I'm doing is I'm parameterizing two different outputs, my total deformation and my average equivalent stress here on all of these bodies. And these are going to be the values that we're looking, these are parameters of interest, so to speak, the values that we want to see how these specifically change when we alter our inputs. So with that said, you enter as many design points as you want to consider. And then when you're done, you have your full design of experiments set up complete. Now, if I scroll all the way to the right over here, I can see that my output parameter columns have their own individual entries here, right? So these values get populated as we solve. I've already solved these, which is why these are here. If you didn't have a solution for a particular design case, then you would see these little lightning bolts like we have over here, which means that this specific case still needs to be solved for, because we don't have results for that case yet. If you want to solve all of your different design points, then what you do is you come up here to the left-hand side in Workbench, and you click on Update All Design Points. And what'll happen is that Workbench will automatically go through, read these different input parameters, and the first thing that it has to do is it has to rebuild the geometry based on all the geometrical input parameters that you defined. If you click on the Show Progress bar while this is solving, it'll give you kind of a status. So if I click on this now, it'll give you a status here to tell you at what point that design is being run at, right? So it'll tell you whether it's building the model, or whether it's meshing, or whether it's solving, etc. And then when it's done, it'll populate the output parameter values that you've defined into the appropriate column for that design point, right? And then once that design point's done, it then moves on to the next one. And it'll keep doing that until you've solved all of your different design points and your design of experiments is complete. The last thing to note here, and perhaps this may be one of the more important things to remember, is that when we run these cases, we have to think about how we want to post-process, right? If all we care about are these output values and we don't necessarily want to look at the contours, so like in mechanical here, this is going to correspond to my design point 0, and I can verify that by going all the way over here to the left and looking at which one of these has this little current thing next to it in parentheses here. That's going to tell me which model I'm looking at. So if I open mechanical, I can see here that I can look at these contours, right, just by clicking on them. And I can see, what the results are outside of just the average values that I've parameterized, right? If I want to be able to do that for each of my design points, then what I have to do is come back here into Workbench and make sure that all the way over here on the right, this little box is checked for all the design points that I want to be able to look at, right? That what this stands for here is retain data, right, or retain results. And so you can see here by default, what happens is that you generate these design points and this box isn't checked, meaning that the only thing that's going to be generated is the actual output from our output parameters. And I can't then go back to design point 1 and look at the contour values of my total deformation and stress. If I do want to do that, then again, I click this box here. So if I were to click this box, then I would have to rerun this now because it doesn't have the result file there. And once I click this box and rerun, what I would be able to do is then right click on this design point and set as current. Once you set as current, that's going to select which design points results you'd like to look at. And then you basically just close mechanical and reopen it, and it'll switch it to that design point that you're trying to consider. So that's how you save the actual result file so that you can look at the contour values while also kind of changing between the different result sets that you want to analyze. As far as setting up your parameterized model, again, this is the most basic way to do so. And this way allows us to consider a lot of different individual design points that we already know the input values for, right? Now, if we wanted to optimize these things, this is where we would go and we would consider using a secondary tool like OptiSlang. And OptiSlang is going to appear on the left-hand side here in a workbench. Oops, sorry, my workbench is kind of frozen here. If I scroll all the way down and then click on OptiSlang here, I can see that I've got these options to use for my OptiSlang study. Again, OptiSlang is not going to be discussed in this video, but if you did want to choose to try and optimize all of my input parameters, right? Like let's say, for example, what we're trying to do is we're trying to minimize the amount of stress that we see on our heat exchanger, right? What OptiSlang allows us to do is it allows us to set that objective or that minimize stress parameter as an objective to use so that as it goes through and does individual studies, let's say it does design point 1, and we notice that the stress is higher than it was from design point 2. In this example, it's not, but just let's say that it is for the sake of imagination. If it sees that the stress is higher, then what it'll do is it'll automatically adjust the next set of input parameters to kind of help you, again, try and minimize the stress. So try and get a lower value for stress. So in essence, it helps you, it's automatically going to help you choose different input values for your design points, and then try and choose the optimal design point such that your objective is met. Now, again, we'll talk about that in our kind of follow-up video here, but just to give you a basic example of the power of OptiSlang, I wanted to give you that brief description. With that said, that brings us to the end of this demonstration. I hope this was helpful. If you have any questions or comments, please feel free to leave them in the comments section of this video, and we'll be happy to address them as we see them. For new requests, you can also leave requests for videos there as well. But otherwise, we'll see you in the next video. Thanks, everybody. Bye.